Welcome to next lecture. In the previous lecture, we discussed single phase full converter, semi converter, continuous and discontinuous conduction with the different cases. After then, we did problems also. Now, there is one more case in single phase full converter. Okay, just for reference, readily I drawn circuit diagram and source voltage waveforms here. So, what is this circuit? Please recollect. Single phase full converter T1, T3, lower half devices T4 and T2. Okay. So for this particular circuit with a constant current load, in our previous lecture we had a detailed analysis. Okay. Now here just a repetition. Let us draw output voltage and output current waveforms. Now, at omega t is equal to alpha, T1, T2 pair of devices will be triggered. At pi plus alpha, T3, T4 pair will be triggered, and 2 pi plus alpha, again T1, T2 pair will be triggered. Okay. Again T1, T2 pair will be triggered. So with this, what was the output voltage waveform we discussed earlier? That was alpha to pi plus alpha. Alpha to pi plus alpha. As T1, T2 pair is in conduction, we discussed that output voltage V0 will be same as that of VAB, that is the source voltage. Follow carefully. One of the important discussion. Pi plus alpha to 2 pi plus alpha, as T3, T4 pair is in conduction, output voltage will be VAB, that is red color sinusoidal. 2 pi plus alpha onwards, output voltage will be VAB, that is blue color sinusoidal. Now from 2 pi to 2 pi plus alpha, it is same as that of 0 to alpha. Okay, this is the output voltage waveform what we discussed in our previous lectures. On the assumption of load current is to be constant. Okay, so on the assumption that load current is a constant, this is a I0 waveform. Okay, and the magnitude of this horizontal line is capital I0, where output current is a constant. Now let us draw two more waveforms. Earlier we have not discussed that. Anyhow, concept was explained. Now I want to draw current flowing through T1, T2 pair. Let us use one symbol for that. Let me call that is a I1. Now, if you look into this circuit diagram, current flowing through T1, T2 pair, I can denote with a symbol I1. Current flowing through T3, T4 pair, let me represent with a symbol I2. Okay, I'm going to draw I2 here. Okay, now you just tell me based on our previous lectures, T1, T2 pair was in conduction from where to where? Alpha to pi plus alpha. Okay, T1, T2 pair was in conduction from alpha to pi plus alpha. In that interval, the current magnitude is I naught. Again, in the next cycle, T1, T2 pair will conduct after 2 pi plus alpha. This is what I1 waveform, which is a current flowing through T1 and T2 pair. Next, T3, T4 pair conducts from 0 to alpha. Next, pi plus alpha to 2 pi plus alpha. Okay. So, in this interval, what is I2 waveform is equal to I dot, right? Till this, nothing new. It is just a recollection. You can also say it is a revision. What we discussed earlier lectures, okay, for single phase full converter. Now, one of the important point to discuss here, yet omega t is equal to alpha. Now, follow carefully here. I1 waveform. What is I1 waveform? I told current flowing through T1, T2 pair. So, current flowing through T1, T2 pair is suddenly changing from 0 to plus I naught. Okay. Similarly, at the same instant, current flowing through T3, T4 pair is suddenly changing from I naught to 0. Strictly speaking, the transition between the pair of devices is not instantaneous. The transition between the pair of these T1, T2 pair and T3, T4 pair is not instantaneous. Reason is the source we discussed earlier. Source side there will be a transformer. Rectifier input will be taken from some transformer circuit, right? So, if you consider the inductive nature of the source by representing with the symbol LS. So, what will be the modification in these waveforms? Okay, present discussion is that. So, we can put heading for this topic is effect of source inductance in single phase full converter. Okay, effect of source inductance in single phase full converter. Now, because of that source inductance, what is the change? What is the change? Current flowing through T3, T4 pair will decrease from I naught to 0, not instantaneously. Now, the red color line will show you that the transition, okay, means T3, T4 pair current will decreases from I naught to 0 slowly, gradually it will decrease rather than suddenly. That is due to inductive nature of the source. In that interval, current flowing through T1, T2 pair will increase from 0 to I naught, okay, 0 to I naught. And this interval, this particular interval can be represented with a symbol called mu, okay, where mu is known as overlap interval. Overlap interval. It is also called commutation angle. It is also called commutation angle because during that interval commutation of thyristors will taking place. Now, in the similar manner, yet pi plus alpha also, what will happen? T1, T2 pair current will decrease from I naught to 0 gradually. T3, T4 pair current will increase from 0 to I naught gradually. Again, this interval is also represented with a symbol called mu, commutation interval. Okay. Similarly, at 2 pi plus alpha again, at 2 pi plus alpha again, T3 T4 pair current will decrease from I0 to 0. T1 T2 pair current will increase from 0 to I0. Okay, this is also overlap interval represented with the symbol called mu. So what is the modification in the circuit analysis? The modification is, when source inductance was not considered, at omega t is equal to alpha and pi plus alpha, the current transition between the pair of thyristors is instantaneous. But due to inductive nature of the source, this transition between the pair of thyristors will take place gradually, and hence some overlap angle, some overlap will come into picture. Okay, that is called overlap interval. During this overlap interval, one pair of devices is going to turn off, and hence it is also named as commutation angle. Okay, so observe carefully here, during this overlap interval, okay, during this overlap interval, what happened? One pair of devices current is decreasing, other pair of devices current is increasing. Whether it is increasing or decreasing, what is the point here? All of the 4 thyristors in this bridge, okay, all of the 4 thyristors in this bridge are in conduction. Now see here, when all of these 4 thyristors are in conduction, we can say that voltage across XY terminals will be 0. Therefore, see, whatever waveform we plotted already, that is, source inductance was not considered. Now suppose if we consider source inductance, let me write like this, with source inductance, okay, with source inductance, then what is the concept? During overlap interval, as all of the 4 thyristors are in conduction, we can say that output voltage will be 0 during overlap interval. As all of the 4 thyristors are in conduction, output voltage will be 0. Okay, therefore now you just think about what is angle at this instant, that is alpha plus mu, isn't it? This is alpha, so alpha plus mu. Next, at pi plus alpha again there is an overlap interval. So during this overlap interval, again output voltage is going to be 0. Therefore, what is angle at this point? Pi plus alpha plus mu. Okay, pi plus alpha plus mu. Next, yet 2 pi plus alpha again there is overlap interval. Therefore, in this overlap interval, output voltage is 0. So I can say here this instant is 2 pi plus alpha. Okay, so if you observe carefully here, what is the modification from when LS was not considered and LS is considered? After considering source inductance, overlap angle come into picture. During overlap angle, all of the 4 thyristors are in conduction. Out of that, one pair of devices current is decreasing, other pair of devices current is increasing. Okay, because of that, all the thyristors in conduction, it resulted into output voltage is to be 0. Okay, so the modified waveform of V0 by taking source inductance into account, it is like this. Okay, so from this waveform, what is our first observation is, by taking source inductance into account, some portion of V0 waveform, now let me take this pulse, some portion of V0 waveform is removing, isn't it? The shaded area is removed. Because of that, what we can say, net area under output voltage waveform is going to reduce. When net area is reduces, what is the consequence? Average output voltage is going to reduce. Okay. Therefore, whenever source inductance is taken into account, the impact on the converter performance is it will reduce average output voltage. Okay. How much voltage it will reduce, that we will see through equations. Before going to that equations, there is one more waveform. Let us see that. The next waveform is source current. Okay, source current. Now if you recollect, what was the procedure we followed in order to draw source current? Now in this circuit, let us take one reference direction for IS. That is what IS. Suppose if IS is flowing as per this direction, we can treat that as positive. If it flows in the opposite direction, then we can treat that as a negative. And in the previous full converter analysis, what we got, whenever T1, T2 pair is in conduction, right, we got source current as a positive. Whenever T3, T4 pair is in conduction, we got source current is to be negative, right? Whenever T1, T2 pair is in conduction, source current is positive. T3, T4 pair is in conduction, source current is a negative. So let us take that point only. Now just refer your previous I1 and I2 waveforms, just now I erased. So you can notice that alpha plus mu to pi plus alpha. I1 waveform was plus I0. What do you mean by I1? That is current flowing through T1, T2 pair. Therefore, alpha plus mu to pi plus alpha, we can say source current is equal to plus I0. Okay. Alpha plus mu to pi plus alpha, we can say source current is equal to plus I0. Right. Next. Pi plus alpha to 2 pi plus, pi plus alpha plus mu, this point, this line, okay, pi plus alpha plus mu to 2 pi plus alpha instead. We have only I2 waveform. I2 means what? Current flowing through T3, T4 pair. So if T3, T4 pair is in conduction, what about a source current? That is minus I0. Okay, therefore in this interval, I can draw source current is equal to minus I0. So 2 pi to 2 pi plus alpha is the same as 0 to alpha, our discussion. So this is what source current waveform. Okay, and next cycle after 2 pi plus alpha plus mu, sorry, this is a plus mu also you need to add. 2 pi plus alpha plus mu, right? So 0 to alpha, source current is minus I0. Alpha plus mu to pi plus alpha, it is plus I0. Pi plus alpha plus mu to this instant 2 pi plus alpha, it is minus I0. 2 pi plus alpha plus mu, again it will plus I0, it will continue. Now our question here is, during overlap interval what will happen? During overlap interval, the transition between pair of thyristors is taking place. In one pair of thyristors current is decreasing, other pair of thyristors current is increasing. So coming to source current point of view, what we can say here, this current will change from minus I0 to plus I0. Observe carefully here. If you consider all the 4 thyristors are operating uniformly, then we can say this function when changing from minus I0 to plus I0, it will cross x-axis exactly in the middle, okay, by assuming that all the 4 thyristors are operating uniformly in the same fashion. Similarly, in this overlap interval, also the source current will cross from positive magnitude to negative magnitude in the middle of that overlap interval. And in this overlap interval, the source current will change from minus I0 to plus I0. It will cross x-axis in the middle. Now, one interesting modification is when source inductance was not considered, source current waveform was square waveform in our previous lecture. When source inductance is considered, what is the source current waveform shape? It is a trapezoidal waveform. Okay, let me write down here. Without LS, source current is square waveform. With LS, very important conclusions. With LS, source current is trapezoidal. Okay, with LS, source current waveform is a trapezoidal. So here again you can get that square waveform. For example, if source inductance is not there, mu value will be 0. If mu value is 0, then this trapezoidal waveform can be approximately considered as square waveform only. Okay, next. So for square waveform, Fourier analysis, what we got, the fundamental component will cross x-axis wherever that square waveform started. For this trapezoidal function, Fourier analysis is a little bit difficult, so we are not going into that Fourier series derivation. I will draw conclusion from that. What is that conclusion? Fundamental component will cross x-axis at these two instants. Therefore, this is how I will get fundamental component. Okay, and here again we will get fundamental component like this. Okay, so this is how fundamental source current, and next cycle it will continue like that, and the previous cycle it will be like this. Okay, so what is important from this fundamental component? Where exactly it will cross x-axis, that is important. That is, I can write alpha plus mu by 2. Okay, alpha plus mu by 2. What is the significance of this zero crossing of fundamental source current? What is the significance? Based on that zero crossing, we can define displacement power factor cos of alpha plus mu by 2. Okay, when source inductance was not there, what was the dPF we had earlier? It was simply cos alpha. Now because of this source inductance, we have mu also, so it can be calculated as cos of alpha plus mu by 2. If mu is equal to 0, then you will get earlier formula, that is cos alpha. So these are the waveforms for single phase full converter by taking source inductance into account. Now let us look into some equations. Before looking into the equations, now observe carefully here. During overlap interval, all four thyristors are in conduction. Therefore, this T1 is in conduction, hence this terminal will appear here. As T4 is also in conduction, this terminal will further appear here. Therefore, voltage at these two terminals, I can simply take that as a 0. So, during overlap interval, we can write down or we can draw equivalent circuit like this. During overlap, so simply I can write during mu. Okay, so this is a source inductance LS, and these two terminals we can simply close with a zero resistance, and this is a source voltage Vs. Okay, this is the source voltage Vs, and source current I can take it as Is, right? Therefore, how can you write down basic circuit equation? Ls multiplied with dis by dt is equal to Vm sin omega t, right? That is Vs. Okay. So I can rearrange this equation as dis, okay, dis is equal to dis is correct only, let me write down a little bit below. Dis is equal to Vm by Ls sin omega t into dt, okay, sin omega t into dt. Now we need to integrate both sides in order to solve this equation. So what are the integration limits? What are the integration limits? Let us see that. So here overlap interval started from alpha. Therefore lower limit could be alpha. Upper limit could be alpha plus mu. Okay. But here x-axis is omega t. Therefore, how can you write lower limit? Omega t is equal to alpha. Upper limit omega t is equal to alpha plus mu. And if you see here, integration is with dt. Therefore, you should write down lower limit in terms of t. So, how to write? T is equal to alpha by omega. Okay, t is equal to alpha by omega. So, upper limit is t is equal to alpha plus mu divided by omega, which is nothing but omega t is equal to alpha, omega t is equal to alpha plus mu. But lower limit in terms of current, I can write alpha and alpha plus mu. So here point is integration for dis is is. What is is value at upper limit? Alpha plus mu. And what is is value at alpha? We need to substitute that. So from the source current waveform, is value at alpha plus mu is a plus I naught. Is value at alpha, that is minus I naught. Therefore I naught minus I naught, okay, is equal to Vm divided by Ls integration for sin omega t is minus cos omega t. As integration is with respect to t, write down in the denominator omega. What are the limits here? T is equal to alpha by omega. Upper limit t is equal to alpha plus mu divided by omega. Therefore here we can get 2 I naught left hand side is equal to Vm divided by omega Ls, okay, Vm divided by omega Ls. Upper limit is minus cos of alpha plus mu. When you substitute t is equal to alpha plus mu by omega, omega will cancel. Lower limit minus of minus, that is plus cos alpha, okay. Or you can also express this equation as I naught is equal to Vm divided by 2 omega Ls multiplied with cos alpha minus cos of alpha plus mu, okay. This is the expression for I naught. This is the expression for I naught. Let me write, this is equation number 1, okay. From this equation we can also write cos of alpha plus mu is equal to cos alpha minus 2 omega Ls divided by Vm into I naught. 2 omega Ls divided by Vm into I naught. Now let us call this equation as equation number 2, okay. So these are the equations that related based on the output current, okay. Now let us look into the equations based on average output voltage. That means first let us find out average output voltage from the waveform. Okay, so if you look into the waveform here, now in order to find average output voltage, we need to integrate this waveform. By looking into this waveform, I can say the periodicity of the waveform is pi. What are the limits for the integration? This instant we can start, that is alpha plus mu, and we need to integrate up to this point. This point is pi plus alpha. Therefore, average output voltage V0 can be written as 1 by periodicity, that is pi. Integration limits are alpha plus mu to pi plus alpha. Blue color sinusoidal equation is Vm sin omega t d omega t. Therefore, this can be further simplified as Vm by pi integration for sin omega t is minus cos omega t, limits from alpha plus mu to pi plus alpha. Okay. Now this can be simplified as Vm by pi upper limit minus cos of pi plus alpha is equal to cos alpha minus of minus plus cos of alpha plus mu. Okay. Now let us call this is equation number 3. Now we can express this in a different form. What is that? Substitute cos of alpha plus mu value into equation 3. Okay, so what we will get? Cos of alpha plus mu value we can have from equation number 2. So if you substitute here, we will get V0 is equal to Vm by pi multiplied with cos alpha plus cos alpha minus 2 omega ls divided by Vm into I0. Okay, then it will give you V0 is equal to 2 Vm by pi multiplied with cos alpha, first term Vm by pi into 2 cos alpha. I can write it like this. Minus, if you look into the second term, Vm and Vm will get cancelled out. Therefore, it will give you 2 omega ls divided by pi multiplied with I0. Okay. So this is, let us call this is equation number 4. Now observe carefully here. Suppose if you recollect from our earlier lectures, average output voltage of single phase full converter, we got that value was 2 Vm by pi cos alpha. Okay. Now from that 2 Vm by pi cos alpha, some number is subtracted. What is that number? 2 omega ls divided by pi into I0. What is the reason for that number is to be subtracted? That is, during overlap interval, by considering source inductance, we have some portion in V0 waveform was removed. Because of that, I told earlier the net average output voltage will reduce. Okay. Therefore, we can say the second term in this equation number 4 is voltage drop due to source inductance is equal to 2 omega ls by pi multiplied with I0. Okay, 2 omega ls by pi multiplied with I0. Now here I would like to tell you one point. In some books it was given as omega ls by pi into I0. I will suggest you please do not follow that. This is a correct procedure. There are some earlier previous gate questions on this formula itself. So even gate key also given as per this formula. Okay, please follow equation number 4 exactly. So the second term in equation number 4 is called voltage drop due to source inductance. Okay, now we can express this equation number 4 something like this. So converter output voltage, it can be represented with some voltage source with a variable symbol. Magnitude is 2Vm by pi cos alpha. Okay, variable source voltage. So that is this 2m by pi cos alpha is a converter voltage. Now this voltage is subtracting by some amount. Okay, what is that amount? 2 omega ls by pi, and some current is flowing through this. Okay, some current is flowing through this, that is a I naught. Therefore, this particular output voltage, let us represent with the VOT. Okay, that is a net terminal voltage. So this particular voltage drop in the DC side we are representing generally can be represented with the RC, where RC is nothing but commutation resistance. Okay, so this is some voltage reduction will be represented with a symbol called RC, a drop, right? Now this is one way of representing equation number 4. Second way of representing equation number 4 is, suppose if we take V naught on y axis, I naught on x axis, equation number 4 can be treated as y is equal to mx plus c line, okay, with a negative slope. What is the slope of this particular line? Minus 2 omega ls divided by pi. Minus 2 omega ls divided by pi. Okay, so converter is expressed in terms of a straight line characteristics like this. Let us take this is a point A and this is a point B. What are the quadrants for operating point A? That is, here a point is located on y axis, means x coordinate is 0. Therefore, I can write here I naught is equal to 0 at this point. Now look into equation number 4. If I naught is equal to 0, we will get V naught is equal to 2Vm by pi cos alpha. 2Vm by pi cos alpha. Now let us write the quadrants for operating point B. On this point, I can say x quadrant is equal to 0. That is, V naught is equal to 0 at point B. Now look into equation number 3. If V naught is equal to 0, we can say that mu value is equal to pi. Just cross check it once. Mu is equal to pi. Why? Suppose if mu is equal to pi, cos of pi minus pi plus alpha will give you minus cos alpha, then it will be 0. If mu is equal to pi, now see this equation number 1. So this term will be minus of minus cos alpha, so 2 cos alpha, 2 and 2 will cancel out. Therefore, we will get I naught is equal to Vm divided by omega ls multiplied with cos alpha. So these are the quadrants for this particular operating point A and B. Okay. So in this way, you can represent the converter circuit, full converter circuit, as an equivalent circuit like this, or a converter characteristics, a straight line like this. Now, for example, from equation 2, follow carefully here, we would like to write 2 omega ls divided by Vm into I naught. Now how can we write it? That is, cos alpha minus cos of alpha plus mu. Okay. Now for example, if you multiply both sides with Vm by pi, then what we will get? Left hand side, let me write down here, 2 omega ls by Vm I naught. Now what I am telling is, I would like to multiply with Vm by pi is equal to right hand side also I will multiply with the same number multiplied with cos alpha minus cos of alpha plus mu. Then what we will have in the left hand side? 2 omega ls divided by pi into I naught, okay, is equal to right hand side Vm divided by pi multiplied with cos alpha minus cos of alpha plus mu. Okay, now you tell me what is this particular term is called? That is voltage reduction. Okay, voltage reduction or voltage drop due to source inductance. Now for example, if you write down a formal statement like this, voltage drop due to source inductance divided by average output voltage at no load. Okay, so what is such a ratio is called voltage drop versus no load voltage. Such a drop is called voltage regulation. Okay, such a drop is called voltage regulation. Therefore, how can you express this voltage regulation? Numerator term, I can use this equation. What is that? Vm by pi multiplied with cos alpha minus cos of alpha plus mu. Denominator V naught at no load. V naught at no load means no load is nothing but I naught is equal to 0. Therefore, by using equation number 4, no load voltage, we can say that 2 Vm by pi into cos alpha. So here Vm by pi will get cancelled out. Hence, regulation is equal to, we will get cos alpha minus cos of alpha plus mu divided by 2 cos alpha. Okay, this is one of the important objective question. In single phase full converter, the expression for voltage regulation is equal to cos alpha minus cos of alpha plus mu divided by 2 cos alpha. For example, if it is a diode bridge, if it is a diode bridge, if it is a diode bridge, what do you mean by that? Alpha is equal to 0 in case of diode bridge. Under such conditions, you can write down regulation is equal to 1 minus cos mu divided by 2. Regulation is equal to 1 minus cos mu divided by 2. Now let us take one example. The figure shown on the screen is an uncontrolled diode bridge rectifier supplied from a source voltage of 220 volt 50 hertz single phase AC source. The load draws a constant current of 14 ampere. The conduction angle of the diode D1 in degree is. Now let us look into the solution. Before starting the solution, I just want to tell that this is not an ammeter. Generally, while doing this problem, students will have a feeling that, sir, what is the reason to connect an ammeter here? It is not an ammeter. Constant load current, sometimes it can be represented like this also. Of course, in our theory, we represented with a rectangular box. but in this problem it is shown as a circle, okay, nothing else. So it depends on author to author. So what is a basic question here? We need to find what is conduction angle of D1. So first, for example, from our earlier discussion, let us draw I1 and I2 waveforms. First, let us take without source inductance. So first, forget about the source inductance. If the source inductance is not there, I1 waveform is from 0 to pi. Okay. Next, pi to 2 pi, I1 current is 0. What is I1 here? I mean, I1 current is nothing but current flowing through D1, D2 pair. Okay. If you want more clarity, you can draw here. This is a I1 and this is a I2. Okay. This is a I2. Next, from 0 to pi, I2 is 0. As D3, D4 is in conduction from pi to 2 pi, we will get I2 waveform in that interval. This is the blue color waveform without source inductance. Now, when source inductance is considered, okay, when source inductance is considered, what is the new parameter that is going to introduce? Obviously, that is a overlap interval. In this overlap interval, what happens? Current flowing in D1, D2 pair will increase from 0 to I0 gradually. Okay. So, before this interval, okay, that is just same as before 2 pi. 0 and 2 pi both are same. Therefore, I can have here, if you take one more cycle before D3, D4 pair current, I should show a decreasing here, right? Similarly, at this place, this current will decrease and this current will increase. So this current will increase here, this current will decrease here. This is the overlap interval denoted with the symbol mu. Okay. So if you draw source current waveform, then what you will get? Source current waveform is I0 here and minus I0 here. Okay. Minus I0 here. I hope you are following. So whenever I1 is equal to I0, in that interval source current is a plus I0. Whenever I2 is equal to I0, what do you mean by I2? Current flowing through D3, D4 pair. When D3, D4 pair is carrying the current, then source current is equal to minus I0. Therefore, instead of a square waveform, we are going to get a trapezoidal function. Therefore, here in this place, this current will change from minus I0 to plus I0, and this current will change from plus I0 to minus I0, and it is going to be like this. Okay. So what are the conducting devices? Just for clarity, if you write down the devices numbers here, 0 to mu, all 4 devices are in conduction. D1, D2, D3, D4. All of the 4 devices are in conduction. And mu to pi, D1, D2 are in conduction. Next, in this interval, D1, D2, D3, D4 devices are in conduction, again during overlap interval. And whenever the source current is minus I0, on what basis we got that conclusion? Based on D3, D4 conduction. So this is how, again, in this overlap interval, all 4 devices are in conduction, right? So this is the conduction sequence of the devices or diodes, right? So what is the conclusion here? Now what is the question basically? How much time a D1 will be in conduction? Not only for D1, you will take any one device, you will have the same answer because all the 4 devices will operate uniformly. Okay. Now observe carefully. D1 is in conduction from 0 to up to this point, it is 180 degree. So 180 plus mu I can say. Okay. Conduction angle for D1 is 180 degree plus mu, because the question is asking in terms of degree, hence I would like to substitute in a degree only. Okay. So we need to calculate mu value basically. Now if you recollect from our earlier discussion, what was the equation we should use for this problem? Cos of alpha plus mu is equal to cos alpha minus 2 omega ls divided by Vm into I naught. Okay. But now the given circuit is a diode bridge, as the circuit is diode bridge, substitute alpha is equal to 0. Okay. Therefore we will get cos mu is equal to cos 0 is 1 minus 2 omega ls divided by Vm into I naught. Okay. So now if you substitute the values, 1 minus 2 into omega is 100 pi multiplied with ls 10 millihenry, 10 into 10 power minus 3 divided by source voltage 220 into root 2, and output current is given as 14 ampere. Okay. So from this we will get simplification, mu value is equal to 44.2 degree. Therefore conduction angle for D1 is equal to 180 degree plus 44.2 degree. Final answer is 224.2 degree. Now let us take another numerical example. A single phase full converter circuit is supplying 3 kilowatt power to a constant current load. The converter is operated at alpha is equal to 30 degree. Source specifications are 230 volt 50 hertz single phase, and source inductance is 1.4 millihenry. We need to calculate commutation angle and RMS value of fundamental component of load current. Now let us look into the solution. So given problem statement, I just put it as a block diagram or circuit diagram like this. So this is a single phase full converter, and constant current load is denoted with a capital I naught symbol, and this is a source voltage. Just for quick reference, I just noted down the data here. So what we need to calculate? Commutation angle, that means mu. Next, RMS value of fundamental source current. So this problem looks very easy, but it is a tricky problem. Follow carefully here. So in this particular case, what is that tricky? Let us see. P0 is given. What do you mean by output power? V0 multiplied with I0, that is 3000 watts. When the load current is a constant, you can say V0 is output power can be defined with V0 into I0. Now we don't know what is V0. Okay, we don't know what is V0. So, and one more thing, what is IS1 value? Okay, what is a IS1 value and what is a mu? If you look into these two values, they need I0 value. They need I0 value. Okay, so from this I can say I0 is equal to 3000 divided by V0, right? But what is V0? V0 is don't know. So if you write down the expression for V0, how can you rearrange this term? Where V0 is equal to 2Vm by pi into cos alpha minus 2 omega ls by pi into I naught. Total multiplied with I naught is equal to 3000. Okay, is equal to 3000. Now, if you substitute the given data 2 into Vm, that is 230 multiplied with root 2 divided by pi into alpha is given as 30 degree. So cos 30, okay, multiplied with I naught minus 2 omega ls, where omega is equal to 100 pi, ls is given 1.4 millihenry, therefore 1.4 divided by 1000 I can write, multiplied with pi, the pi is in the denominator, okay, into this term multiplied with I naught square is equal to 3000, okay, is equal to 3000. Now we have one quadratic equation, okay. So what is this quadratic equation? Simplification is 179.33 into I naught minus 0.28 I naught square minus 3000 is equal to 0. Okay. So by solving this quadratic equation, I will get two values, 17.19 ampere and 631.16 ampere. Okay, 631.16 ampere. Now what is the tricky condition here? We got two answers, both are positive, right? You need to select one reasonable value. Okay, so but mathematically both are true. As per the quadratic equation solution, both are true. But I will select the first value. I will neglect the second value. What is the reason? Suppose if you select this second value, the current rating of devices will be very high. Just for 3 kilowatt load, 623 ampere rating is not required. Therefore, you can proceed with the 17.19 ampere. Now, you can get the first question, that is mu calculation. Cos of alpha plus mu is equal to cos alpha minus 2 omega ls divided by Vm into I naught. Okay, so cos 30 minus 2 into omega is 100 pi, source inductance 1.4 into 10 power minus 3, okay, denominator Vm, that is 230 multiplied with root 2. Now I naught value we are substituting 17.19 ampere. Okay, therefore from this I got alpha plus mu value is equal to 34.96 degree. Therefore mu is equal to this minus alpha. I will get 4.96 degree. This is the answer. Okay, this is the answer. Now if you remember our previous waveform analysis, I just shown that in the source current waveform, the zero crossing of fundamental source current, I have not given any expression for the peak value of that fundamental source current, because if you do the Fourier series analysis, of course you will get, but that is a very lengthy procedure. Instead of that, you can do in a simple way, that is, see, for example, if I say output power denoted with the symbol P naught, then input power I can write it as P in. Input power I can write it as a P in. Therefore, by assuming this particular thyristor block as ideal block, power electronic circuit has to satisfy power balance equation, right? what is the power balance equation? What is a power balance equation? For example, if I write power balance equation, that is input power given to the bridge should be equal to output power to that load. So how can you express input power? Vs1 into Is1 into cos of alpha plus mu by 2, that is cos phi 1, is equal to 3000, that is what given in the problem data, right? Now what is the reason I am expressing in terms of fundamental components? Because source current is not a pure sinusoidal. In this particular problem, it is trapezoidal function. Therefore, you have to substitute in terms of fundamentals only. Therefore, what is Is1 now? 3000 divided by Vs1 is 230 multiplied with cos of alpha is given as 30 degree plus mu value we got 4.96 divided by 2. So if you calculate, the simplification is, I got the answer here, 15.5 ampere. Okay, this is RMS value of fundamental source current. This is the final answer. Now let us take another numerical example, that is a single phase full bridge fully controlled thyristor rectifier feeds a load comprising a 10 ohm resistance in series with a very large inductance. So you can say that load current is a constant because of that statement. Next, the rectifier is fed from an ideal 230 volt 50 hertz sinusoidal source through cables which have negligible internal resistance, means source resistance is neglected, and total inductance of 2.28 millihenry. Okay, so the total source side inductance is represented with the 2.28 millihenry. Now, if thyristors are triggered at an angle 45 degree, alpha is equal to 45 degree, find the commutation overlap angle. Now let us look into the solution. This question was given in the recent GATE 2020 exam. Okay, so this problem is based on source inductance. Now here few statements we need to understand. Load is a resistance of 10 ohm is connected in series with a large inductance. What do you mean by that? Load current can be approximately treated that as a constant. Okay, and of course I naught value is not given, but it need in the intermediate calculations. So source voltage is 230 volt, and now source side total inductance is represented as a lumped parameter of 2.28 millihenry. Therefore what we can write here, I naught is equal to basically V naught by R. Okay, I naught is equal to basically V naught by R. Or from this we can write V naught is equal to R into I naught. That means 10 multiplied with I naught. Okay, 10 multiplied with the I naught. But as per full converter circuit with source inductance, what is average output voltage? 2 Vm by pi cos alpha minus 2 omega Ls by pi multiplied with I naught. Okay, so V naught is equal to 2 Vm by pi cos alpha minus 2 omega Ls by pi into I naught. So here from the previous conclusion here I can write V naught is equal to 10 multiplied with I naught. 10 multiplied with I naught is equal to 2 into source voltage peak value 230 multiplied with root 2 divided by pi into cos 45. So I can write it is 1 by root 2 minus 2 into 100 pi. because source frequency is 50 Hertz. Hence, we can have omega is equal to 100 pi divided by pi into source inductance 2.28 divided by 1000, okay, multiplied with I naught. I naught is not given here. So this simplification is, I have this value 146.42 minus this total value is 0.456 into I naught, okay. Therefore, how can you write I naught value 146.42 divided by 10.456, okay, 10.456. This simplification is, I naught value is given that 14 ampere, okay. I got I naught is equal to 14 ampere. The data is framed to get I naught is equal to 14 ampere. But final question is, we need to calculate mu value. So how can you express that? Cos of alpha plus mu is equal to cos alpha minus 2 omega ls by pi into I naught, okay. As alpha is 45 degree, you can write cos 45 is equal to 1 by root 2 minus 2 into omega is 100 pi into ls is 2.28 divided by 1000 into pi multiplied with I naught value, we got it 14 ampere, okay. So this value I got it as 0.645. 0.645. So from that, if you write alpha plus mu value is equal to cos inverse 0.645. This value is equal to 49.8 degree, okay. Therefore, finally we will get overlap angle is equal to 49.8 minus 45 will give you 4.8 degree, okay. This is the final answer. So in this lecture we discussed about effect of source inductance in single phase full converter, and we discussed a good amount of problems on that, okay. So with this I would like to conclude this lecture. Thank you.